In this video, I will walk you through free response question number 4 from the 2010 AP Calculus exam. This problem is primarily about area and volume. Let R be the region in the first quadrant bounded by the graph of y equals 2 times the square root of x, the horizontal line y equals 6, and the y-axis, as shown in the figure above. Part A. Find the area of R. If you integrate with respect to x, you can find the area between two curves by integrating the top function minus the bottom function. In this case, the top function is 6, and the bottom function is 2 radical x. From left to right, region R goes from 0 to 9, so these are the limits of integration. Let's write the square root of x as x to the 1/2 power. Integrating term by term, the antiderivative of 6 is 6x. And I'm just going to bring down the minus 2 for now. For the x to the 1/2 power, I increase the exponent by 1. So this will become x to the 3/2 power. And then I divide by the new exponent. Dividing by 3 over 2 is the same thing as multiplying by 2 over 3. So I will go ahead and apply the limits of integration from 0 to 9, but 2 times 2 over 3 is 4 over 3. So let's simplify that. So we need to find the value at 9 minus the value at 0. So here we have the value at 9 minus the value at 0. Because both terms have an x in it, it's easy to see that the value at 0 will just be 0. Of course, 6 times 9 is 54. And I'm just going to leave the 4 over 3 for a moment. 3 over 2. This is power over root. So this is the same thing as the square root of 9 and then the third power. The square root of 9 is 3. 3 to the third power is 27. So I have 4 over 3 times 27. 3 goes into 27 9 times, and 4 times 9 is 36. So the area of R is 18. I should point out that for a free response question, I could leave my answer like this if I wanted to. Part B. Write but do not evaluate an integral expression that gives the volume of the solid generated when R is rotated about the horizontal line y equals 7. When you rotate region R around the line y equals 7, you get a solid that's a little bit like a sideways volcano with this tunnel going through the center of it. If you take a slice of the solid, it forms a washer, a disc with a hole in it. We can use washers like this one to calculate the volume of the solid. It is a 3-step process. Step 1 is to find an expression for both radii of the washer. We will need an expression for the radius of the outer disc, which I will call big R, and the radius of the inner disc, which I will call small r. Let's start with the big radius. When the radius is vertical, you can find an expression by subtracting the top function minus the bottom function. In this case, that's 7 minus 2 radical x. So here's my expression for the big radius. Now let's find an expression for the small radius. Again, we can find this by subtracting the top function minus the bottom function. In this case, the top function is 7, and the bottom function is 6. But of course, 7 minus 6 is just 1. So this is my expression for the small radius. Step 2 is to find an expression for the area of the washer. You can visualize the area of a washer as the area of a big disk minus the area of a small disk. In other words, the area of a washer is pi big R squared minus pi small r squared. Since we already have an expression for big R and small r, we can transform this into an expression for the area of the washer by writing pi big R squared minus pi small r squared. The last step is to find an expression for the volume of the solid by integrating the area of a washer. Since we already have an expression for the area of a washer, all we have to do is integrate this. When you integrate the area of a washer, you are adding up all of the washers to form the volume. Because the washers are stacked up from left to right, we will integrate with respect to x. And because the washers are stacked up between 0 and 9, these are the limits of integration. The directions say write but do not evaluate an expression for the volume of the solid. So this is the answer. Part C, region R is the base of a solid. For each y, where y is between 0 and 6, the cross-section of the solid taken perpendicular to the y-axis is a rectangle whose height is 3 times the length of its base in region R. Write but do not evaluate an integral expression that gives the volume of the solid. When they say that region R is the base of a solid, I want you to picture an oddly shaped loaf of bread that is sitting on region R. In other words, the footprint of the loaf of bread is region R, and we're looking down from above. When they mention cross-sections perpendicular to the y-axis, they are talking about slices like this one. We can use slices to calculate the volume of the solid. However, before we get started, because these slices are stacked vertically, ultimately we will have to integrate with respect to y. So we need to rewrite this function in terms of y. So right now we have 2 radical x is equal to y. Let's solve this for x. We need to divide both sides by 2, so that gives us the square root of x is equal to y divided by 2. And then we can get rid of the radical by squaring both sides. So that will give us x is equal to y over 2 squared, which we can probably better write as y squared over 4. Using slices to calculate the volume is a 3-step process. Step 1 is to find an expression for the base of a single slice, which I will call b. When the slices are horizontal, you can find the length of the base by subtracting the function on the right minus the function on the left. So in this case, that will be y squared over 4 minus 0. Of course, we don't need the 0, so this is my expression for the length of the base of a single slice. Step 2 is to find an expression for the area of a single slice. We are told that each cross-section is a rectangle. So if we grab a slice and pull it out and look at it, it's going to look like this. We've been talking about the base of a single slice, and that base is right here. We are told that the height of the rectangle is 3 times the length of the base. So if the base is b, the height will be 3b. But we need an expression for the area. The area is base times height, so that will be b times 3b, which is 3b squared. In step 1, we wrote an expression for the length of the base of a single slice. But now we need to transform this into an expression for the area of a single slice. But we know that the area will be 3b squared. So I can turn this into an area expression by writing 3b squared. The last step is to find an expression for the volume of the solid by integrating the area of a single slice. Since I already have an expression for the area, all I have to do to find volume is integrate. Because these slices are stacked vertically, I will integrate with respect to y. And because the slices go between 0 and 6, these are the limits of integration. So we could say the volume of the solid is given by this integral. Or we could simplify a little bit. If we square this, we will get y to the 4th power over 16. So we could also say the volume of the solid is given by this expression.